All right, welcome back. So, I know I said I was going to go through a bunch of shapes, but I realized, wouldn't it be a little more descriptive to actually put normals on the shapes so we can see make them look 3D, basically. And so with that in mind, let's investigate normals with ray marching. Now, imagine that we have some shape, and it looks a little bit like this. We're looking at it side on. Who knows? There's my shape. Now, this is coming from its signed distance field. So everywhere along this surface, that signed distance field has a value of 0. This is what's called a level curve or a level surface. It's also called an isosurface or something. And what we could do is also visualize a bunch of other points. I'm simplifying a little bit, but let's say that these are exterior to the surface. So this is the set of points which have a distance of 1 from the surface, and the set of points which have a distance of 2 and 3, and it doesn't really matter. And then inside, we have the interior. So this is the set of points, distance -1, distance -2, -3, and so on and so on. Okay, now why is this important? Well, if anyone's done multivariate calculus, you'll know that a surface or a level surface or a level curve has a grad vector, and the grad vector points in the direction of greatest increase. So it looks like that. There we go. So at this point, we would have to walk in 3D in this direction to get away from the surface. We have a tangent vector, which is completely inside the surface, and that's the direction of no change. This is the direction of maximum change, and it turns out that these are orthogonal. Okay, so let me just put, grad f. Grad f is, let me just write this. Grad f is orthogonal to, how am I going to write this? I'll just put t for tangent. So tangent is going to follow this surface. Anyway, what was I getting at? Well, grad f will be the partial derivatives of the function with respect to each of its parameters, just like that. Right. So I'm not sure if this makes sense or not, but what this comes down to is, remember, f is the signed distance field. What we need to do is measure or approximate the partial derivatives of the signed distance field with respect to x, y, and z, and that will give us the normal vector. That's sort of cool. Now what this comes down to, let me pick this point here, and I'll say, okay, I want to measure or approximate the partial derivative. Let's say this is x here. We'll just do a 2D version. Now what I would do is, it's completely up to you. You could take this point, go a little bit to the right, and measure the distance. That will give you some sort of value, and by a finite difference, you would get some approximation of the x partial. But to improve that approximation, you could also take an equally spaced point to the left, measure that, and that would give you an improved approximation. So that's what I'm going to do here. I'm going to say that the x partial is approximately that. Now, you could be looking at this and saying, hey, well, guess what? We should also be scaling this, dividing by the interval width, which is 2 delta x. Yeah, that's 100% correct. But as you'll see, because the intervals are always going to be the same, you'll have each of these components divided by 2 delta, where delta is the interval, like the epsilon width that we're choosing here. But all that will do is basically scale down the vector, and when we throw this into the code, we'll actually be normalizing it anyway, which will remove that scaling factor. Anyway, so I'll leave that. We'll jump into the code. Okay, so here we are. We've got our shapes from before. Look, I don't know what's happening with my voice. it just suddenly broke, and I can't sort of cough it good again, so I'm just gonna keep proceeding with this weird voice. Okay, so I'm gonna have to do a few things. I am going to modify this so that we have a single function which just gives us the distance to the scene. That's what I'll call it. Okay, and that will basically be taking the role of this stuff. So I'll just go ahead and grab all of this. Just neaten it up a little bit. And now you might notice a refactoring that I made. Instead of dealing with the ray, I'm just dealing with the ray's position. Because remember, in ray tracing, you solve a mathematical equation where you need to know where the ray is and where you're looking. But in ray marching, you're literally just dealing with distances. So I'm actually going to make that modification here as well. Okay, that looks great. And now I'll just go right back to the main function, and I'll replace all of this with the distance function. Okay, so if this is all working correctly, then we should see the same thing. But we've just farmed that out to a different function. It's not neatly wrapped up. We can use that later on when we are getting the normals. Let's just restart that. Okay. Now, can you imagine what it is? I think I know. I think I forgot to return the distance. Yes, we've got the distance. And let's just try that again. Whoops. There we go. Excellent. Right, so, damn, what is with my voice? Let's now make a function which will use this distance function to approximate the normal vectors at every point on the spheres. Just as a quality of life, I'm defining these, I call them ruler vectors because they just sort of point out in the fundamental directions that I want to measure. They all have the same length. They're just pushing in different axes. Okay, so now I'm going to approximate the normal components. There we go, that's the central difference approximation for the x component of the normal, and really we'll just do the same thing in y and z. All that remains now is to combine those components into a new vector and normalize it to make sure that it is normalized, of course. That should now be correct. And so what I'll do as a means of testing this is I will invoke that function right up here where we set the pixel. So instead of setting that to the pixel color, instead of setting the pixel color to a constant value like this, I will display the normal. Now, there are reasons we would want to do this instead of applying a simple directional lighting, because I want to confirm that the components of the normal are being set correctly. Of course, at the moment we could have positives or negatives, so we'll go ahead and add 1 to each of those. That'll stick everything between 0 and 2. And then we will multiply everything down by a factor of 0.5. That'll just stick it between 0 and 1. Now, provided I've made no errors, that should now be working. As you can see, it looks to be... Oh, my voice is back. Oh, excellent. Okay, these ones look pretty good. This one looks good, a little bit discontinuous. This one, I feel like this is not the ideal configuration to view that subtraction. We're not seeing this space in here, which is being carved out. So what I'm going to do is I'm just going to modify these spheres so that we'll be looking at them dead on, but one sphere will be carving out the face of the other. Just like that. Give that a go. And there we go. Now we can see the sphere subtraction did correctly occur. Cool. So, I mean, that's it for this session. Short and sweet. I don't know what's going on with my voice. It's weird. But that'll be it. So, thanks as always, and I'll see you again soon. Bye.